For our last feature today, I'm revisiting the subject of pee, or P, if you like. We seem to talk about this a lot, especially peers for some reason. What makes it yellow, what new drugs are in it, if we can get useful things from it. And I'm happy to welcome Dyllon Randall, one of my favourite mad professors, to talk about collecting our pee to make bricks and fertilizer.
Today I'll be talking about our urine to fertilizer work. If we focus on the resources present in urine, specifically in the wastewater coming from our herds, we see that the urine makes up only about 1% of the wastewater volume. Yet it contains over 80% of the nitrogen, 70% of the potassium, and 50% of the phosphorus. So the first problem is, how do we collect this valuable urine? So we can use what is called a no-mix toilet, and like the name suggests, the toilets do not mix feces and urine. Laufen has launched the Save toilet, which makes the separation even easier. We can also collect the urine directly from urinals, and we can collect urine from commercial buildings, sporting events, any busy area. Urine collection has also been implemented in many locations, such as Irvak in Switzerland. A new suburb in Paris will implement urine collection. And the Xyro has a urine collection system in the new headquarters in South Africa. So the second problem to overcome is the potential nitrogen loss from urine. About 90% of the nitrogen present in urine is fixed as urea. Now this urea degrades in the presence of an enzyme called urease to produce carbon dioxide, ammonia, or ammonium, depending on the pH of the solution. We can prevent this from happening by operating at a low pH or by operating at a high pH. And this allowed us to develop a passive dosing system whereby a base, such as calcium hydroxide, is pre-dosed into a collection tank, and then someone simply pees into it. A small amount of the base will dissolve, you add more urine, and a little more dissolves, and so on. Provided you have enough base in the collection tank, the pH will stay high and prevent the loss of nitrogen. This allowed us to develop a fertilizer-producing urine, and this is the very first prototype. It consists of a removable container, a funnel, with a splashback, to which you add calcium hydroxide, and then you simply add urine. So each of these urinals can produce about 276 grams of fertilizer with a 96% phosphorus recovery. We are now collaborating with a UK-based waterless urinal company called Dwarfaway to further develop these urinals. The third problem is, how do we efficiently remove water from urine, considering that it's about 95% water? So we can do this using reverse osmosis, where we produce water and a liquid fertilizer concentrate, typically considered a brine. So why reverse osmosis? Well, it is an established technology, it is commercially scalable, and it uses substantially less energy than phase change water removal technologies. Here is a comparison of the energy requirements for phase change technologies compared to reverse osmosis for water removal from urine. So when we focus on using reverse osmosis to produce water, it can be seen as an expensive technology because the product water is so relatively cheap. However, if we use reverse osmosis to produce a niche liquid fertilizer, we see that it can quickly become more lucrative. So our lab-scale urine treatment process has successfully removed 70% of the water from urine, achieved a 99.8% phosphorus recovery, 80% nitrogen recovery, and a 97% potassium recovery. We have now designed and commissioned a full-scale process, which we aim to use to optimize the process, verify the fertilizer quality, and perform a detailed economic analysis. We can also produce a wide range of other higher value products from urine, some of which we have already done so. Essentially, what we are doing is developing a circular sanitation system where we recover value from human urine. I leave you with this quote by Buckminster Fuller. Pollution is nothing but the resources we are not harvesting. We allow them to be dispersed because we've been ignorant of their value. Thank you.
Mining finite resources to make fertilizer makes no sense when we are all walking P and N dispensers. Dylan, thank you so much for making using what we all produce every day sound so obvious and so sane.